What happens when we invoke the fit method of a k-nearest neighbors model? What's happening? What's happening when we call fit? Well, in general, what happens when we use the fit method? What's happening? In any model, it doesn't matter if we're looking at KNN or logistic regression, support vector machines, what is happening when we use the fit method? When we use the fit method, we're training the model with the training data, and the model is looking for the best set of model parameters. Trying to reduce some sort of cost function, usually the case, figure out the best set of model parameters. But in k-nearest neighbors, what's your thoughts? What's your thoughts with k-nearest neighbors? Is there any model parameters, or what are the model parameters for k-nearest neighbors? It's a very simple algorithm. It's a very simple model. And it really has no regular parameters to it. And in fact, the way the model makes predictions, it just says, let me look for the k-nearest neighbors. So when we do the fit method of a k-nearest neighbors, nothing is really going on. In fact, that's a very quick process. But let's consider what is happening when we use the predict method. What is happening when we use the predict method of k-nearest neighbors? Well, when we call predict, what the model is doing is that it's taking the observation that you want to make prediction on, it's placing it in this p-dimensional space, and it's calculating the distances from each training point. And then it repeats for another observation in which you want to make a prediction on. So given what's happening, we'll describe what's happening during the fit and predict, which of these two steps do you think is the most computationally expensive? It's in the predict method where it's most computationally expensive because it has to calculate those distances. So training is negligible. Its prediction is going to take a long time. And this is one of the problems with k-nearest neighbors. What do you think will happen? What do you think is the time complexity for prediction? When we analyze algorithms, one of the things we want to ask ourselves is, what is the time complexity of this algorithm? In other words, how does it scale? How does the training time scale as I increase the number of inputs? In this particular case, we're going to talk about machine learning. We're concerned about what is the training time, the prediction time as I scale my size of my data set. In other words, if I double my training data, will my prediction time double? Will it stay the same? Would it increase by a factor of 4? What will happen? What is the time complexity? How does the training time scale, prediction time scale as a function of my training size? Now for prediction, the time complexity is order n, which makes sense because what you got to do is if you have a larger data set, you have to calculate more of those distances, and it's a linear scale. If I double the number of training points, then I have to double the number of calculations for distance. So the time complexity for prediction is linear. And the other thing we got to consider is what's going to happen is that the k-nearest neighbors can be quick to fit, but it might take a long time to make a prediction, specifically when we have a large amount of training data. And that might be a problem because what if whatever service I'm doing, I want to make a quick prediction. Yes, the training time might take a long time, but once I have a trained model, guess what? Ideally, I don't have to retrain it anymore, so I can just make predictions with it. But if it's slow to make predictions, perhaps I don't want to use this model for my application. So if prediction time is a concern of yours, you want to have a very short prediction time, then perhaps you shouldn't use k-nearest neighbors. Now let's consider memory. Let's consider memory usage of our model. In order for you to make a prediction with k-nearest neighbors, guess what? It has to have the entire training set in memory. It has to carry around the training set. And this is different from other models. Let's compare it with something like linear regression or logistic regression. You give it the training data with the labels, then the model learns what are the good model coefficients, what are the good beta coefficients to use. When you make predictions, you don't need the original training data to make predictions. Yes, you had to use it to get the beta coefficients. But once you have the beta coefficients, that's all you need to make a prediction. I have the beta coefficients, give me the features for the observation, then I can make a prediction. No need to rely on the training data that I use to learn from. With k-nearest neighbors, guess what? If you want to make a prediction, do you need the training data? Do you need the original training data? And the unfortunate answer is yes, you need the original training data because that's how the model works. You put the observation in the space of all the training points, calculate the distances, make the prediction. So as my training size increases, then my memory demand for this model is also going to increase. And that's going to be a problem. If I have a very large data set, then I might not have enough memory for what I want to do. So k-nearest neighbors has problems with memory requirements, specifically when our data set gets too large. So in general, if prediction times are a concern of yours, you want to have fast predictions, you might stay away from k-nearest neighbors. If you have a very large data set, then you have also problems with k-nearest neighbors to go with k-nearest neighbors because it has to carry around the entire training set. That's not ideal. Nonetheless, it's a very simple algorithm, and sometimes it works surprisingly well. So I wouldn't issue it for some other model. You should always try it out, see how it performs. Of course, if you have too many observations, you may not bother trying to see how well it performs.